Okay, so welcome back. We are continuing with loss study of microstrip line. Why we are giving so much importance on loss? Because at millimeter wave frequencies, it creates the main problem for any MMIC. So let's see more studies. So these we have calculated these losses by using full wave simulator. So we are considering three different thickness of substrates: 15 micrometer thickness, 30 micrometer thickness and 45 micrometer thickness of BCB substrate. It is popular at millimeter wave frequencies or even at terahertz frequencies, and typical tan delta value for 100 gigahertz and 400 gigahertz is 0.002. It's high but not that bad, and 0.005, this is 700 gigahertz to almost 1 terahertz, and the corresponding epsilon r, it's 2.57, and it remains approximately constant over 100 gigahertz to 1 terahertz. And typical metal thickness we are considering for all these three cases is 1 micrometer. Now if I change the substrate thickness 15 micrometer to 45 micrometer, and if we have only 50 ohm microstrip line, in that case obviously the width of the microstrip line will be different. If we have a thicker substrate, we have to increase W to make it 50 ohm. So in 15 micrometer, the thickness is the width of microstrip line is 42 micrometer, and it increases to 130 micrometer when we are considering a 45 micrometer thick BCB substrate. And now let us first calculate what are the cutoff frequencies. We have 4 expressions, and if we calculate FT1 to FT4 for these 3 different substrate, what we see in each and every case FT3. What do you remember what is FT3? This is the threshold frequency of transverse resonance, and we are considering it for that given 50 ohm line in the substrate. So FT3, it is minimum among all these 4 for each and every case. For the first substrate, it's coming 1890 gigahertz. For the second substrate, it's 945 gigahertz, and for the third substrate with thickness 45 micrometer, since it is having the widest line, it is having the minimum FT3. So the third substrate we can't use, let's say, above 600 gigahertz. Now let us look at the loss plots. So alpha dB per millimeter, considering a smooth surface, we are not considering any surface roughness. If we add surface roughness, so loss will be much more, 2 to 3 times than this. Now you see, for 15 micrometer substrate, loss is much higher compared to that 45 micrometer thick substrate. Why? For 15 micrometer, the width of microstrip line is 42 micrometer, so it's thinner. So that's why conductor loss is highest for this 50 ohm line on 15 micrometer. This is over 75 to 110 gigahertz. Now if I further increase the frequency, we are considering terahertz band 350 to 400 gigahertz. You see, for 15 micrometer, previously loss was 0.25 to 0.3, now it increases to almost 0.55 dB per millimeter. If I further increase the frequency, what will happen? It increases to 0.6 approximately dB per millimeter. And remember, this is without any surface roughness. So if I add same value of surface roughness with these 3 cases, then the effect will be more prominent at higher frequencies. Why? Because at higher frequencies we have smaller delta S, and we have seen in the correction factor that if it depends on the surface roughness with respect to delta S. So, if I go back here, you can see we are plotting it only for 15 micrometer and 30 micrometer, and that 45 micrometer is absent here. Why? Because for 45 micrometer we will be facing that transverse resonance phenomena, because already we have calculated FT3 is 613 gigahertz for the third case. Let us consider a special scenario, microstrip couple 9. We use microstrip couple 9 whenever we go for the component design, components like couplers, filters, and we deal with even mode and odd mode analysis of the couple lines. So, let us see what is that. We have two coupled microstrip line. We can excite this coupled microstrip line by using two RF signals. In one case it can be in same phase, and in the second case it is in opposite phase, 180 degree phase difference between these two signals. So, the first case, when the two signals are in same phase, we call it even mode condition, and the second case we call odd mode condition. Let me show you the time domain propagation. So, you can see the strips, and in this figure we are showing the propagation direction is y, and we are placing two millimeter wave sources at this edge left hand side. So, here, right here. So, let us first consider the even mode excitation. That means these two sources, they are in same phase. Now, we are considering the electromagnetic wave propagation in y direction, a time frame when this pulse it just reaches the midpoint of this microstrip line, and the shape of the pulse we are considering Gaussian shape. Now, you can see the plot of electric field just below the microstrip line in even mode excitation. This is then we are having mostly Ez component, and you can see the Gaussian profile. In even mode they are in the same direction, and not only that, if you look carefully at the tip of this, so if I just zoom in these tip points, so in even mode what will happen, the inner tips they are little down compared to the outermost tips. You can say we are facing somewhat repelling effect between these two different signals. That is why the inner tips are little down compared to the two outer tips. And in the second case, the same my coupled microstrip line, but in this case what we are doing, we are exciting them by using opposite phase signal. So, one signal in this direction and the another one having 180 degree phase difference in opposite direction. So, now we are plotting the electric field just below this strip when it reaches the mid plane, and you see the electric fields they are in opposite direction, one having plus Ez component and another one having minus Ez component. And if I compare in this case the tips values, then inner tips those are at higher potential. So, in this case the inner tips it will be at higher values, and the outer tips that will be lower. So, you can say some here we are facing somewhat attractive phenomena. Now, let us go back to the previous one. So, what happened here? In even mode condition, when we are exciting by the source having same phase component, the electric field, this is the plot of electric fields on a cross sectional plane. You can see the black color microstrips, and this black color line it represents the ground. So, the direction of electric field in same direction, and there won't be any coupling between these two strips. So, no electric field exists from left to right hand side strip. So, we can model this system by using two capacitors as C11 it represents the first line and C22 it represents the second line, and then effective CE we can consider these two lines with ground together as a single transmission line system. So, this single transmission line system obviously it will be associated with some beta, alpha and some characteristics impedance. So, we call the characteristics impedance when we are exciting in even mode Z0E or even mode characteristics impedance. Similarly, in odd mode we can define another characteristics impedance obviously which will be different since the electric field orientation it's changing, and in that case we will call it Z0O or odd mode characteristics impedance. And in this two different scenario, beta or phase constant it will be different. Why? Let us again go back to the circuit diagram. So, in odd mode excitation you can see in one case this for the left strip the electric field below the strip it is in this direction, and for the right strip it is in bottom direction, and not only that we have electric field coupling between these two strips. For this figure it shows that electric field right to left strip. So, we can model this system by three capacitors C11, C22. In addition to that, due to this coupling electric field coupling we can represent it by two more capacitors C12 twice C12. Actually the capacitance is C12, we are just breaking it into two parts. So, now one interesting phenomena we see, if I compare the electric field plot for these two cases, left hand side we have electric field mostly confined inside the substrate, and right hand side fringing field is more in air. Now, if I calculate epsilon E for both of these two cases, obviously it will be different. So, effective epsilon for the even mode configuration it will be higher compared to that in odd mode excitation. Why? Because we have mostly the electromagnetic wave propagation through dielectric, and here right hand side as the field plot shows we have fringing fields also which we can't neglect in air. So, the conclusion is that epsilon E in even mode it is much higher compared to the epsilon O in odd mode. What is the problem we face due to that? If epsilon E is different, that means lambda g will be different. If lambda g different, phase velocities will be different, we will be having dispersion effect. So, for even mode, since epsilon E is higher, small length will show more beta. So, if I consider let us say a fixed length of 5 millimeter microstrip line for left hand side case and right hand side case. So, for left hand side if the 5 millimeter length it represents some electrical length, equivalent electrical length let us say 180 degree at some given frequency. For the right hand side, since epsilon O is smaller, it will represent smaller length, it is not 180 degree at that frequency, but something much smaller than that. So, due to that we face problem when we design components, because in practice if we excite a couple line system, we can always divide it into two parts, even mode component part and the odd mode component parts, and the these two excitation they coexist and we will be having dispersion. One more interesting observation here, for the even mode case we do not have any electric field from left strip to right strip. So, if I consider a mid plane which is perpendicular to this and it is placed just in between these two strips, then no electric field is passing through that plane. Not only that, the electric field left hand side and the right hand side, it becomes parallel. So, we can call this plane a PMC or open circuit condition. Similarly, for the right hand side, if I place a mid plane here, which is the plane of symmetry, so electric field on that plane, it is perpendicular. That means it behaves as a short circuit or PEC. So, even mode condition, we call it sometimes the open circuit condition, and odd mode condition, we call it sometimes the short circuit condition. One more observation: since no electric field is from left to right, then the coupling effect, there is coupling effect, because if I look at this plot, the outer tips are higher compared to the inner tips. So, there is coupling effect, and for this one, then this coupling, it might be through magnetic field. So, for even mode, we call it magnetic coupling, and right side we can see it clearly. We have electric field from right strip to left strip. So, the coupling is due to electric field and we call it electric coupling. So, two important conclusions: one, in even mode we can place one PMC between these two strips, and in odd mode it should be PEC, and not only that, in even mode the coupling is due to magnetic field. So, we call it magnetic coupling, and for odd mode we call it electric coupling. So, in practice, then how we can improve it, that how we can avoid the dispersion problem. There are some remedies. So, let me discuss one of them. Let us say we have a couple line system. I am drawing the top view. So, this is the left strip and this is the right strip. Now, if I plot the surface density of surface current component on left strip and right strip, for even mode and odd mode, they will have different variation. So, in even mode, this current will be more concentrated on outer edge. So, this is for the even mode scenario, and in odd mode we have some sort of attractive effect. So, the current will be more on the inner edges. So, this green line, this is the current distribution for odd mode excitation. Now, what we have seen, that for a given length, the equivalent electrical length theta, which is beta into L. So, L is the length of this strip. So, this theta will be higher for even mode excitation. So, theta E is more than theta O. We have to, if we can increase theta O, so that theta E, it becomes equal to theta O, in that case we can avoid dispersion. How we can do it? There are many ways. One of them, noting down that electric field inside air is more in odd mode configuration. What we do? We use some dielectric overlay on this strip, so that in even mode there will be some field inside this overlay. Now, depending on the dielectric constant of that overlay, we have to control the thickness by using any full wave simulator, so that theta e it becomes equal to theta naught. This is one way. Another popular way, noting down that the current distribution is different, so you can say it in different way. Since the current distribution for the odd mode is higher at the inner edges, so if I perturb the inner edge, most probably it is going to perturb the odd mode characteristics, right. If I do any perturbation, if I add any perturbation on the outer edges, it is going to affect mainly my even mode characteristics. Now, noting down theta e is more than theta naught, what people do, intentionally they will cut some groups. So, the structure, resultant structure, it looks somewhat like this with groups. So, what we are doing here? We are introducing some groups here, so that the effective current path in odd mode it increases. You see, now it becomes longer, right. So, we have to then tune the depth of this group and the width of this group, so that this theta e it becomes nearly equal to theta naught, and it is not going to affect my even mode excitation, since we are doing at the inner edges. So, this is another popular method to avoid that dispersion effect. Okay, so next let us start CPW line, coplanar waveguide. It comes in 1960s. So, let me draw a coplanar strip line first, how it looks. So, we have a central conductor which is a central strips, and it's separated by from two ground strips, and together they sits on a dielectric layer. You can consider it as a coupled slot. This is the cross sectional view. So, inside we have electric field. If you remember that odd mode and even mode excitation, so we prefer even mode excitation, so that these two extreme grounds they will be at same potential, and in that case the electric field configuration will be like this. So, again we see that we have some fringing field in air and some fields inside the dielectric. So, we will be facing dispersion problem, just like microstrip line. And in this case, if I change frequency, again just like the microstrip line, epsilon e it will change. We can also control the characteristics impedance. We have some standard closed form expressions. So, if I decrease this slot width, characteristics impedance it decreases. We have similar FT1, FT2, FT3 and FT4 for the CPW line as well. So, in most of the cases what we do, its width, effective width including the ground left to right, it should be less than lambda g by 4 to avoid any transverse resonance and to avoid any parasitic mode. But you see, if I use a open structure, it's a semi-open structure that support quasi TEM mode. Now, if you remember that transverse electric surface wave mode, in that case we have the dominant electric field component which is in this direction, and so we will be having coupling from CPW mode to TE0 surface wave mode, which has no cutoff frequency, and this coupling will increase if I increase the thickness of the substrate. So, how to avoid this? So, in most of the time for MMIC, the CPW line is not preferred, since you have to maintain the spacing for this fringing field as well as for the dielectric, because finally at the end of the day we have to go for some packaging, and packaging we do by using some metal box. And now if the metal wall, let us say it represents the metal wall of the packaging, if it is close to CPW line, then obviously there will be coupling between the CPW mode and this metal, and the mode characteristics will change. So, we have to maintain a minimum separation for that, and that separation depends on the signal line width, the slot width, and as well as the dielectric constant and the thickness of the substrate. Similarly, at the bottom side we can't place the packaging wall just attached to the substrate. So, we have a problem due to packaging. So, usually a pure CPW line, it is used in semiconductor industry, like for in silicon fabrication, germanium fabrication, or gallium arsenide fabrication. Again, silicon, germanium or gallium arsenide, they follow different fabrication process. For example, gallium arsenide fabrication, it starts with backside metallization. Silicon germanium, it does not have any backplane metallization. It starts with bulk P type or N type material. So, in PCB form using laminates, usually we don't use open CPW line like this. So, what we use? We use a grounded CPW line or ground backed CPW line as shown in this figure. So, you can identify the top layer CPW line, W, this is shown as the width of the signal line, WG, this is the width of the ground, and we have one additional metal layer, it is the ground plane of the CPW line. And now you see, at least in one side we can directly place our packaging wall, and on top of this, of course, again we have to maintain some minimum separation. So, we will take a short break, then we will discuss on the ground back CPW line. Thank you.